세미나에 앞서서 폴란 ENT의 고문이신 당국대학교 건축학부 명예교수 김회서 박사님의 인사말을 먼저 들어보도록 하겠습니다. 박수로 환영해 주시면 감사드립니다.
네, 오늘 이렇게 참가해 주셔서 대단히 감사합니다. 지금 오늘 세계적으로 상당히 연구와 또 우리가 지금 필요한 앞으로의 4차 산업에 필요한 하나의 건물이라든가 그 밖에 여러 부분의 에너지 절약이라는 것이 상당히 중요시되고 있습니다. 저는 32년 동안 당국대학에서 교편을 잡고 특히 저는 이제 건축의 환경 설비를 했기 때문에 건물 에너지에 이제 전공을 해서 오랫동안 여러 군데 많은 자문과 또 역할을 해봤습니다. 오늘 아마 이런 새로운 하나의 유리, 이때까지 우리가 알고 있던 유리하고는 좀 다르죠. 굉장히 디테일하면서 굉장히 세밀하고 또 상당히 아주 많은 하나의 에너지를 절약할 수 있는 그런 하나의 중요한 그런 하나의 클래스를 갖다 오늘 발표하실 거라고 보는데 아마 우리나라 국내에서도 앞으로 우리가 지금 녹색 인증이라든가 여러 가지 이제 건축에서도 제로 에너지 또는 이런 여러 가지를 하고 있습니다. 그래서 이런 부분에서 역할과 또한 여러 가지 유리가 들어가는 많은 수케이스라든가 또는 하나의 여러 가지 하나의 유리로서의 어떤 역할을 하는 데서 에너지 전략 관여를 한다 할 수 있다는 것 이런 것들이 상당히 획기적인 거라고 생각합니다. 아무튼 오늘 여러분 와서 많이 보여주시고 많이 홍보해 주시고 또 앞으로도 우리 국내에서도 이런 하나의 산업이 활성화되고 또 우리 측근에 항상 옆에 보일 수 있도록 그렇게 많은 노력을 해주시기를 감사합니다. 감사합니다.
자, 그럼 오늘 세미나를 본격적으로 시작하겠고요. 오늘 세미나 발표자는 진공유리 권위자인 시드니대학교의 코서 박사님이고요. 코서 박사님은 이번이 첫 번째 한국 방문이라고 합니다. 큰 박수로 환영해 주시면 감사하겠습니다.
Thank you for coming today. My name is Cenk Kocer. I'm a researcher at the University of Sydney, and I've been a part of the vacuum glazing insulating group there since about when the project began at the university. Today I'd like to give the seminar a little bit less of the technical, but a bit more of the background in terms of the history of the vacuum glazing, plus a little bit of looking at the state of art and commercialization today, in terms of what's happening with vacuum glazing, who's doing what, and where it's happening as well. Okay? Now, if I speak too quickly, please say so. If there's any questions, please feel free to ask me as we go along. So I think most of you know what a thermos flask is. Thermos flasks, we make them because we like to keep cold things cold and hot things hot. I think maybe some of you will know of Sir Dewar. He was someone, a researcher back in the 1900s. He had a reason to do some research to try and keep liquid nitrogen in a bottle. So he wanted a jar which would allow him to keep liquid nitrogen cold for a very long period of time. And to do that, he sort of invented the idea of a double skin jar where he evacuates the space between the two skins. And at that stage, he even realized that he should add a silver coating onto one of the surfaces to reduce more of the heat loss. So that was the invention of the thermos flask. But to be honest, very soon after that, the idea from some people that you could make the same device flat, so that you could have a flat panel insulating device, came about quite quickly in a very short period of time. So in terms of the vacuum glazing that we even see today, in terms of all the components and the detail, the inventiveness of that goes all the way back to 1913, when the first patent appears in the literature about a flat panel insulating device. And between 1913 and 1987, there's actually very little scientific research, but a lot of inventiveness. And there are numerous patents, and they actually speak to most of the, if not all, of the issues surrounding the vacuum glazing. About the spaces, the little pillars between the glass, about the edge, about the fact that these pillars or spaces will actually move and what to do about that movement, about how to evacuate the gap between the glass. So the technology actually has a very long history, all the way back until the 1913 period. But up until about 87, as I said, there was very little academic research. And around about this time, okay, back maybe a year or two later, the leader of the group I joined, Professor Richard Collins, was at a conference. And there was a group in America who was looking at vacuum glazings. And at this conference, they made a point of saying that making the vacuum glazing was almost impossible. And when they discussed why, the main issue they found was making the edge seal, that is bonding the two pieces of glass together, which is this bond here at the edge. Richard Collins happened to have worked for the electronics industry before he came to the university, and he knew of a new product called solder glass, something that was invented to be able to make vacuum tubes quite quickly and easily. He obtained some of that material from his colleague, and within a month, he was able to make small vacuum glazing panels. Very small, fits in your hand, but he was able to hermetically seal the two pieces, and he was able to pump out the glass through a pump out tube. Similar technique that was used in those days, and we're talking about the late 80s, to make CRT tubes or televisions. So this was the birth of the vacuum glazing invention at the university. Within a year or two, and I joined the group in 1992, 93, this was the actual design that the group decided on. So we have two pieces of glass. We have a solder glass edge seal, which provides a rigid and hermetic seal between the glass. And remember, what we mean by hermetic is we mean no gas goes in and no gas comes back out, okay? Not for the lifetime of the device, which is more than 25 years. And to be able to hold the two pieces of glass apart, because when we remove the air and we produce the vacuum, the glass sheets will want to touch. So we position small pillars or spacers. They're usually 0.5 millimeter in diameter, about 0.2 millimeters in height, and there is an array of them to support the panels. We have a hole in one corner and a little tube we call the pump out tube to actually do the evacuation. And this is the original vacuum glazing invention from the University of Sydney. So soon after, in the 1992-93, when the invention was being finalised in the group, we of course looked for commercial partners. This is a picture from '95. This is me. I don't know if you can tell. I look about the same. This is Richard Collins in the centre, and some of you may know of Professor Jack Tang. This is Professor Jack Tang, who also worked in the group. He returned back to China, and many of the technology or companies that make vacuum glazing in China essentially owe him for the information that he provided. And the rest of the group, well, it's all the workers at that period between 92 and about 1999 where all the work that was done. From 95, we worked with NSG up until about 2000 as well to take our invention to the mass production stage. So, actually, I usually forget to mention this. The question is, will come about later as well, why is not vacuum glazing, if it's this old, everywhere right now in all the buildings? So one easy way to understand why it's not, but NSG was interested, is that at that stage in the mid-1990s, the Japanese government had intentions to have a certain type of building in Japan retrofitted. They wanted more insulation out of these buildings, and the windows were a critical element. But due to the design of the building, a double glazing, was not usable. The window frame could not be changed, and therefore that type of thick panel could not be inserted. So NSG was looking for a thin panel or thin profile insulating panel with good, transmission of light to use in these buildings. And that's where the relationship between our group and NSG actually flourished, because essentially there was no other device for them. Everything else that they needed in terms of U value needed to be 16 or 20 millimeters thick, and only the vacuum glazing has a profile that's basically in those days 6 millimeters. So this is why NSG took up the technology and why they spent quite a lot of time, including having to replace the factory once, because I'll be honest, our group wasn't perfect. Even though we invented it and we understood a lot, we made some mistakes. And in correcting those mistakes, NSG, being the partner, spent a lot of effort and a lot of money making sure the factory would also work to the new technology or to the changes that we make. So they persevered, even though in the beginning many of the NSG executive, let's say, would have thought that it's not a money-making product. At the end of the day, though, it's turned out to be one of their best performing products since then until now. So their production rates are on the order of 500,000 and their demand is still greater than their production capacity. It's one of their best performing products overall, out of all the products that they make. So, of course, though, insulating a building is not new. I mean, people have realized, especially in cold climate regions, and I can feel the temperature here every day, that Korea is one of the cold climate zones. Double glazings or insulating windows is a common technology. And so in the beginning though, we started with low E coatings, right? Everybody saw the advantage of changing single glass and using a good low E coated glass. But of course, as you can see with this progression, and it continues today, we want better and better performance as we go. We would like the glass to reach the same thermal performance as the rest of the building envelope, which means this progression of U value getting lower and lower continues today. And at the moment, you could say that we can go from low E coated glass to the double, and we can go to a triple, and we can go to what today we call the thin multi-layer or the thin triple, which is a very wide gas gap of something like 120, 150 millimeters, but there are multiple thin glass layers to essentially create maximum 15 millimeter volumes, and that way no convection loss. So this type of window is actually projected from the existing technology, and you can get very low U values. But of course what I want you to see is also the disadvantage that comes with it, which is the window is thick. It will require special frames. And of course there's an effect on the solar heat gain, and at the end of the day, if very good coatings are also used, it affects the light transmission too. We can of course try to say that we could use other gases. Instead of air, we can use argon. Instead of argon, we can use krypton, xenon. But again, there's no positive gain when we change anything. And in changing the gases or anything else, the disadvantage is, for example, in this case, cost. There are other durability issues with the IGU in that there is some pumping effects that force gases in and out, which we don't want. And so there is a list of pros and cons in terms of the existing technology. And what we wanted the vacuum glazing to do is to try and solve some of those issues. So I'll get to the cons of the VIG towards the end, but the pro part of the VIG is that one, it's thin. So we use a vacuum, not a gas. So in that sense, the thermal performance of our windows has no dependency on thickness. So we like to make the gap size very, very thin, something like 0.1 or 0.2 millimeters. We can use quite thin glass. And because of that, and the U value being on the order of what a triple is, we can stick to only 2 sheets of glass. That means we have a light, thin profile unit with a good U value. We also, because of the vacuum and the advantage it gives us, we don't have to always use the best low E coating, which means our light transmission and also solar heat gain can remain quite high. So I've got 1 or 2 complicated slides, okay? So please forgive me. This is a complicated slide. So I think my laser is not working now. Sorry, but my battery's run out. So if you look at this plot, the left axis, the y-axis shows you the U value, which is the thermal conductance, air to air, of a vacuum glazing. And down the bottom, which is the x-axis, that's the combined emittance. So when we talk about the radiation between the glass, we talk about combined emittance. That's the emissivity of both the surfaces. So there's a table up the top left. Surface 2 and 3 are the inside surfaces. And you can see coatings in terms of 0.2 is a type of pyrolytic coating, and 0.03, something like a good sputtered double or triple silver coating. And what you can see is that, of course, as the coatings get better, and radiation is the most important process to stop, and in the vacuum glazing, it's the same as the IGU, and yes, we need a good coating. So we try to have really good coatings, and you can see that we can get the U value down. Each of those plots though also show you that we have two other processes in a vacuum glazing. Those two other processes depend on the pillars. So the size of the pillar, if the pillar or spacer between the glass becomes very big, because it's touching both sheets of glass, more heat will travel through. So we want to make the pillars small. Also, it's the number of pillars. So NSG's spacer product uses a spacing or array spacing of 20 millimeters, but we can take the pillars, 20 millimeters, and we can make them 30 or 40 millimeter spacing as well, and that reduces the heat flow. And you can see that when we do that, we get these three plots. And you can see that from the current NSG spacer product and what was our original invention at the university, we have a U value near 1, just a little bit higher. But the U value can go down basically below 0.2 if we wanted to. I'll let that sink in. Is there any questions?
Is it true that 0.2 or below 0.2
Yes?
in terms of U value?
Yes. Center of glazing? Yes. And I'll answer the question you're thinking about in the next slide, okay? So there's 2 points I want you to see before I move to the next slide. Oh, thank you. Oh, is it working? No, it's dead. It's dead. Very, very weak. It's okay. It's okay. So the two things I want you to see from this graph is first, there's something we call a diminishing reward. Okay? You can see that as the numbers go down, they slow down in how much they change. So making the pillars, 60 millimeters apart and then saying, well, let's make the pillars 100 millimeters apart, it doesn't help anymore. So the effort and money you have to spend to change the properties or the components, it doesn't give you much of a reward. So we're looking at basically being somewhere in this area in terms of the lowest performance, okay? If you're thinking about how low can we go, we're talking about somewhere around here, 0.25, 0.3. Maybe you could go a little bit lower, yes, but trying means you have to put a lot more effort in. So the second point is, and where the effort comes in, is the stresses. So there's one important factor with the vacuum glazing. Since we create a vacuum, we have atmospheric pressure that acts on the glass. That's 10 tons per square meter. 10 tons per square meter. So that means that as you do things like make the pillars smaller or move them apart, as you actually make the thickness of the glass thinner, you actually increase the stress on the glass. So choosing a U value has to be balanced with the strength of the unit. So the answer, I think, from what your question really is that if you do want to go to 0.2, then you have to be very careful about what is the strength of the product that you have now. But we have one advantage, one really good advantage. If there's anyone who can say, okay, I can make an IGU of this U value, I can always say, without any problems, that I can make another type of window with a better U value. And that type of window we would call a hybrid vacuum glazing. And that is, we can take any sheet out of an IGU and we can put a VIG in its place. Yes, it will be heavier again, 3 sheets of glass, and yes, it'll be thick, but the combined purpose of gas and the VIG means that we can actually head towards 0.1, right? But that's still center of glass. And I think everybody here, or most of you, can accept that at the end of the day, we do need to talk about the frame as well. Great, thank you. Yes. So the answer is, if you want to go to low U values, you can. And it is the choice of the design of the product that's important, okay? So when we look at what happens in the VIG, we get stresses in these pillars, we get stresses from the contact of the pillars to the glass, and we get stresses at the edge and on top because of the bending that happens, okay? Since between the pillars the glass is unsupported, the glass will bend and produces stresses all through the glass. And we have to be very wary of that. It's one of the areas that's actually my specialty in the group, and that is looking at the elements that create stress and the strength of glass. And we know that if you're not careful when you're designing the product, well, you end up with these cracks in the glass, cracks around the pillars, and even catastrophic failure because of the edge and because of the way the edge is actually placed into the frame too. But if I can make a very bold statement, okay, The science and engineering of vacuum glazings, the technology is done. It's, for us, it's complete. We understand it very well. There's no innovation there for us, for anyone, to be honest. I mean, there's innovation in changing components, but there's no innovation in the design. We understand the limits, and we understand what glass thickness, what pillar size, what edge spacing from the first pillar to the edge, what all of that means. And there is a set of rules that need to be followed. And if you follow them, you can design a product which will withstand all of the rigors of where you want to use it. And that could be residential, it could be commercial, it could be 1 meter size panes, it could be 4 meter size panes. So I want you to know from me that you should have confidence in the design of the vacuum glazing. Whether the manufacturer has followed those rules, that's a different question, right? But, and we'll discuss this in the next couple of slides, the point is that in the future we will have the standards and the certifications which will make sure that the industry follows those rules. So first of all is the manufacturing mode. And so there are lots of manufacturers at the moment, and essentially there's 2 types of manufacturing. So I put the basic 4, but they're still in 2 types. And the first type is that you produce the vacuum glazing product and you evacuate the product directly at the product. So 1 evacuation point for each product and you evacuate. The other one, and it's most commonly known as the inline process, like a coating line, you basically evacuate the whole, not just 1, maybe even multiple, all at the same time. And you don't need, in that case, some sort of hole or port or some sort of entry point into the sample itself. So the other 2, and that's what we call the fixed batch, and that's what we use at the university originally, pardon me. And the other one is the inline layer. So this is a sort of example of an inline layer. This is an example of a batch. So there's 2 other types which are sort of a mix or a hybrid of the 2, okay? You can see the batch is where there is actually a carousel or a rack. Samples go there and they basically move in, here's the rack again, and go through the layer or the other and come out with the samples all finished. So what I'd like you to see from this though is one very important point. So most people think of the vacuum glazing manufacturing line as something new. It's also, in a sense, it's not very new. So most of the technology steps are based on things we've done before. Vacuum tubes, televisions, plasma displays, and most of all, 80% of a vacuum glazing production line is the same as an IGU line. So one of the interactions that the reason I'm here in Korea and interacting and collaborating with Fulan is to look at the concept of IGU manufacturers cannot disappear. IGU factories will not shut down. There are essentially only 3 steps that are different between an IGU production line and a vacuum glazing production line. So to have the correct machinery essentially attach onto an existing IGU line is actually the best solution for producing a vacuum glazing product. Right? Cutting, cleaning, inspecting, pairing, and even the idea of putting spacers in an IGU line, putting spacers in a vacuum glazing, dispensing sealant, dispensing solid glass, these are all pretty much aligned with each other. And so one of the new inventions will be, in a sense, is about the production process, trying to bring the 2 processes together and take advantage of that, and most important to that, to try to lower the cost. So if we look at who's doing vacuum glazing, so I've tried to put a little map here. By the way, it's not perfect, okay? I may be a couple of factories off here and there, but here's a map and it shows pretty much the activity across the world. You can see here's Korea. I've got blue squares for commercial activity, startups and research. And in Korea, I think there's 1 for each, which is basically Egon, Fulan, and there is a university group that's doing some work with solder glass. But you can see that the majority of factories and startups are still in China. They are very fluid with money. And so it's a very nice place if you have a new technology to try and progress. But activities in the US and also in Europe are quite intense at the moment. You have to remember that the policies, and in Australia too, are leading to what we call not 5-star, not 6-star, but 7-star energy ratings. So essentially, even in Sydney, which is a moderate climate, we're not winter at all. We don't get any colder than about 15 degrees in the middle of winter, and it's sunny pretty much every day. But we have a requirement from this year that new houses have to have double glazed windows. And that's phenomenal in a moderate climate. And most people, even in buildings in Sydney, would open the windows in the middle of winter for fresh air. So the rest of the world is even more severe. So the policies will continue to change. So in terms of these products though, as I said, the vacuum glazing is not a new technology. So the point is what's being done. So the first thing to look at is actually the edge seal. So the traditional edge seal, which we used and which made the first vacuum glazing possible, is solder glass. And solder glass is very nice. It bonds very nice to glass. It's very easy to use. It's rigid, provides strength, and it's reasonably costed as well. But in those days, it was lead-based solder glass. So what we want is lead-free solder glass, and if possible, lower temperature. The original solder glass we used worked near 500 degrees. The newer ones work at near 300 degrees. So we save a lot of time and money by lowering the temperature. You can see here, Panasonic Japan has a new technology, but it's still solder glass, but it's lead-free and low temperature. We have a company in China called Leaders, which is also parallel with Landvac in China. They use the metal edge seal. That's a 2-step process of putting metal solder onto glass. We have a company, it's a conglomerate, but basically led in Italy, and they're actually producing currently, they invented this a couple of years ago, a polymer-based material to provide an edge seal. It still needs to be heated for curing, but actually it is a more simpler material to use than solder glass or metal you could say, but it is much newer in technology and does have a lifetime issue. And then we have something very unique in America where they're trying to use pure materials only, and that is bonding pure aluminium foil to glass. And that allows some recyclability of the window when the time comes. This is a much newer technology though and has a little bit more time to go. So the other one is the spaces. And as I said, we can change the shape of the spaces, we can change the number of spaces or pillars, but we can also change the materials. Remember, the conductivity of the pillar affects how much heat will go through. So our traditional material was always metal because metal pillars are simple to produce and they're quite good in the tolerance of their size and shape. But there are printed glass and ceramic. There are independent single pillar ceramic. There's actually something we call a laser feature. Corning invented a way to essentially use a laser to heat up locally glass so that it will expand. So this feature you see here is actually the inside of the glass that has been modified by the laser. This black part is the actual expanded part of the laser, leaving a little dimple or a little protrusion. And that acts like a spacer between the panes where we put them together. And then there's actually, for metal and ceramic, there's geometry changes. There's spheres, there's annulus, and people even cut holes in these to make a C-shaped pillar as well. All of them have advantages and disadvantages. And one of the primary issues is how to take the tiny little pillar and put it on the glass. So that's a part of some of the issues or innovation in the production process that can still happen today. Same as all the other technologies in the past, electronic technologies like vacuum tubes and TVs, one of the most important things about a vacuum device is to keep the vacuum stable. So most people talk about good vacuum and bad vacuum when it comes to vacuum glazing. Actually, it's not the way to talk about it. We have a very hard pressure point. That is 1 millitorr. If we go above that to even 3 or 4 millitorr, the actual performance of the vacuum glazing essentially degrades to 0. It's just a piece of glass, and you'll know that. If we go below 1 millitorr, it doesn't change the performance at all. We can go 1,000,000 times lower, and actually the performance of the vacuum glazing is going to stay the same. And the reason is that at 1 millitorr, the residual conductance from the gas is basically 0 already. Okay? Now once we create the vacuum though, in that environment, things inside the glass will actually move to the surface and then come out. That diffusion process will make the vacuum unstable, which means performance will change over time. And so what we use is a material called a getter. So same as the IGU has a desiccant, we have an active metal called a getter. And the getter's job is to take the water and the hydrocarbons that emerge out of the glass surface and to essentially capture them. Right now, most of the VIG units, including ours, use what we call a pill getter, which looks like a round disc in the corner of the sample. But for example, there's a paste version, comes like toothpaste, and you just basically dispense a line. And there's actually a wire version, which comes like a wire and you put it at the edge. Some companies like these two because the getter is then in the edge, and when you put the sample into the frame, you don't see it. But there is some advantage in the capacity of using a round one and how you activate it, how you get that getter going. So what I want you to have seen right now, if you haven't, in the last 4 slides, is that the components, we have quite a varied choice. And the number of people actually producing vacuum glazing and doing it in a way that, these vacuum glazings are not exploding or breaking or dying over short periods of time, it's quite large. And the history of where the idea of the technology, the research and development of the technology comes from is quite long. So again, the vacuum glazing is not an emerging technology. It's not new, it's actually old. We have reasons, policies and a few others, why it hasn't become a household product yet. But essentially for the future, that's its destiny. So let's look at why it might be the case. So I put a list of windows up here. These numbers, these U values in imperial and metric and the solar heat gain is actually for the window plus the frame, okay? So please have a quick look at what 1 to 8 is. So 7 and 8 are 2 types of vacuum glazing in good and very good insulating frames. And 5 and 6 are triple, and 2, 3, 4 are double, and 1 is just ordinary plus, okay? I think everyone can accept the numbers. So now what I'm going to do is put 2 graphs. One is going to show the energy use of a typical home in Minnesota in the US, which is quite a cold climate area, okay? Winter temperatures go to -20 very often. And then the second graph on the right is going to be for Washington, DC. Not such a cold place, okay? And the graph is going to show you the U value, and it's going to show you the solar heat gain, and the lines that you will see is going to basically be the full energy use over 1 year in that house, okay? And on those 2 graphs, essentially I put the windows and what type of energy they would actually be using if they had those windows. So there's the U value of the window. Let's say normal glass U value near 5, and this is its solar heat gain, and this is the sort of energy you'd be using, somewhere between 126 to 130 gigajoules of energy for the year, right, for Minnesota. But if you went down towards the triple and the VIG, you can see the energy use is much, much less. This black line, based on the house gaining energy from sun and losing back energy through the window, that black line is the net return point. So if we're below the black line, the building is actually going to gain energy from the sun rather than lose it back to the outside. And you can see that the vacuum glazing comes very close to actually providing that solution. Of course, it's very different when we look at a moderate climate, but you can still see that the vacuum glazing is performing very well, comparable to a triple and even better in some sense. So essentially the point here is that the vacuum glazing being light and thin, what it does is it provides quite a high solar heat gain for a low U value. So the confidence point in terms of using the product right now for the industry and user would be something along the lines of, 1, having policies that mandate better windows for buildings, but 2nd, having standards and certifications that define the quality of the product itself. So right now, policies are not something I can affect. That's something for governments. But I am involved with the ISO technical group for working on glass and vacuum vacuum windows. There are also groups at the NFRC, the CEN in Europe, and the ASTM has 2 groups now. We've progressed the ISO group, so there are 2 standards. These 2 standards, and I'll show you in a second, talk to different areas of the vacuum glazing, but they all already define performance. And we're currently working on, I'm sorry, this is overwritten, Part 4, which is actually looking at the strength of a vacuum glazer, specifically for impact. So the ISO standards essentially have already spoken to being able to measure the thermal performance of the vacuum glazing to a standard level. Also to be able to do weather tests and soundproofing tests. It also talks to being able to define the quality that is acceptable for a minimum thermomechanical performance. That is, the performance you expect for a set temperature difference, so that you don't essentially have the windows breaking once you have cold weather. And the impact case, once we are finished with it, probably at the end of this year, middle of next year, we'll talk to the fact that if there's any human impact or outside debris impact, that the VIG will also survive that case. And so it will define a minimum requirement. So if you pick a U value, it will define the thickness of glass, the type of pillar that you can have for a specific size of window. I mean, this is already something we have in the standards for IGUs, for laminates, and other glass products, and so it will follow the same line. So there are plenty of examples. I've only put a few up here. To be honest, there are a lot of residential and commercial buildings that already have vacuum glazings in them. And I've been lucky that I've seen many of them now, and I've seen, especially in Japan, I've actually managed to see vacuum glazings when I didn't expect it. I wasn't there for work, and I was there in a hotel or restaurant and happened to look, and I could tell from the way the glass looks that it was an NSG product. And I could see, wow, people are using vacuum glazings. And you can buy a vacuum glazing in Japan at a home center. It's not a specialty product anymore. So, but I'll point to 3 things which I said, IGUs have pros and cons. Maybe for a vacuum glazing, there are a couple of cons, as in a couple of, let's call them not nice things or negative points, okay? But they're not too bad. The first one I'll reiterate, and that is a vacuum glazing is always under stress. So if you don't design it correctly, it will break. That's one of its negative aspects. But, that depends on design. But the other parts of this, and these are not really bad negatives. So the first one is, it's the frame. So the edge effect on a VIG is different to an IGU. So to be honest, if you are putting a VIG into a building and your point is to really insulate the building, then you need to think about the frame. And to be honest, I think that also counts for IGUs. Nowadays, just putting an insulating window is not the point, especially for windows below 1 meter square. Combining the effect of the frame U value needs to be considered. Secondly, let's talk about, this plot here looks very messy, but it's actually the sound transmission loss against frequency. And there's different monolithic and VIG samples here. Especially in America, when I go to certain talks, sometimes someone will say, oh, do you remember in science doing the vacuum bell test, where you put a clock inside a jar and you suck all the air out and then the clock rings and you can't hear it. And then they say, well, vacuum glazing is a vacuum, so it's no sound will get through. I wish, but it doesn't work that way. It's not as simple, it's much more complicated. There is advantage in terms of sound insulation for a vacuum glazing. It's a little bit more frequency dependent. As a hybrid, you could tune and get a certain insulation if you really want, but it's not perfect, okay? Remember, the 2 pieces of glass are coupled together through atmospheric pressure and the pillars. And therefore, if you push on one side, both sheets will move, and that's what sound pressure does. So it won't be perfectly insulating. And so the insulation levels are sort of similar to IGUs and a little bit better when you make a hybrid. And the last one is this one. And this one's not necessarily negative because it will happen with the triple as well, triple IGUs or even well-known IGUs, and that is on a really cold night, because the outside glass is quite insulated and more the temperature of the outside, you can get frost forming. what's interesting with the VIG is please remember that the spaces or pillars are thermal breaks. So the pillars themselves are actually more close to the temperature of the inside. So the frost will melt where the pillars are, so we won't get frost, but we'll get coconuts. So that's one unique aspect of when vacuum glazings perform well. Okay, so let me conclude. So what I want to do with this, and I hope I've done it for you, and that is I wanted you to gain some confidence in that the vacuum glazing is not a new technology, it's not emerging, it actually has a very long history, there's a lot of research and development, the performance levels are known, the negative issues are well known, we can actually follow a set of well-defined rules to make a good, sustainable product. What we want to really do today is to see that the product is used. And one aspect of that is to be able to come up with innovative production processes that provide a way for the IGU industry to actually pick up the technology and keep the cost low. Essentially, costs right now, many of you might know, could be high. But I'll be honest with you, a good VIG line today should be able to make product that's at least the same price as a good triple, not more expensive. And it should aim to get close to the double. But that means using good components. It means doing a low temperature process. It means having a much more automated production line. And if you do that, and remember that, especially for example for retrofitting, you don't need to change the frames all the time. So that means the whole cost of changing the windows could be cheaper with a vacuum glazing than changing into an IGU where you need IGU frames as well. Thank you.
Q&A는 좀 평소에 쓰는 언어도 아니고 좀 말이 빨라서 좀 이해를 저는 좀 많이 못하는 것 같은데 혹시 궁금한 사항이라든가 뭐 이렇게 좀 이해가 안 됐던 부분 아니면 뭐 발표 내용은 없었지만 진공유리에 대해서 궁금한 사항이 있으면은 꼭 이 자리에서 질문을 하셔서 좀 이렇게 좀 이해를 하고 가시면 좋을 것 같아요. 질문을 받도록 하겠습니다. 질문 있으신 분.
한국말로 질문하도 됩니다.
네네 여기 김명욱 박사 플란에 김명욱
우리말로
박사
하시면
통역을
가능한 의미를 전달하도록 하겠습니다.
그 진공의 필러 있지 않습니까?
예.
그게 가장 이상적인 두께가 어느 정도입니까?
아, 그거는 제가 다음 발표할 때 하면서 좀 얘기를 해드리도록 하겠습니다.
아마 그 다음 발표 때 집중적으로 되실 것 같아요.
제가 조금 다음 발표를 또 할까요? 예. 또 다른 질문 뭐 예를 들면 지금 말씀하시면 제가 할 때 또 참고로 해서 할 수 있는 것도 말씀드리기도 할게요. 지금 안 듣는다고 하시고요. 예.
한국말로 하겠습니다.
예.
뭐 진공 복충유리의 장점에 대해서는
예.
많이들 알고 계실 것 같아요.
예.
그러니까 유밸류라고 아까
예.
말씀하실 때 우리가 많이 사용하는
예.
거죠.
예.
그러니까 낮은 유밸류를 얻을 수 있는 것을
예.
좀 더 얇게 전체 글라스 두께를
예.
전체 글라스 두께를 얇게
예.
그리고 더 가볍게
예.
접근할 수 있다는 것에 대해서는 뭐 다들 공감을 하실 겁니다. 근데
예.
이제 이것을 이제 실질적으로 매스 프로덕션으로 이제
예.
가는 데 있어서의 허들도 많이들 느끼고 계실 거예요. 그 허들 중에 가장 큰 것이 이제 제조업입니다.
예.
예. 그 닥터 코스는 뭐 어쨌든 더블 글레이징하고 비슷한 수준까지도 제조원가를 이론적으로
예.
낮출 수 있다고 주장을 하시는데
예.
기본적으로 단위 면적당 제조 원가는 어쨌든 에너지가 더 드는 부분이
맞습니다.
부분으로
맞습니다.
그 부분을 어떻게 극복을 할 것인가 첫 번째는
예.
궁금하고요. 두 번째는
예.
신뢰성과 관련된
예.
신뢰성과 관련된 문제인데 문제 어쨌든 시뮬레이션을 하신
예.
방법을 사용을 하셔갖고
예.
어쨌든 그 필라 주변에 있는 스트레스를 이제
예.
분산시킬 수
예.
있는 방법에 대해서 얘기해 주신 것 같은데 실제 상업적 유리에서는
예.
완벽하게 이론적으로 평평한 유리를 만들 수는 없습니다.
예.
더군다나 진공 유리 같은 경우에는 강화된 유리를 사용해야
예.
되기 때문에 강화하는 과정에서
예.
이제 우리가 흔히 롤 웨이브라고
예,
하는
예,
게 있을 수 있고 만국이라는 게 있을 수 있기
예.
때문에 필라 개개인에 걸리는
예.
스트레스가 조금씩 다를 거고요.
예.
그 스트레스로부터 발생되는 허츠 프레저가
예.
조금씩 다를 수 있을 겁니다.
예, 예.
이런 부분들이 실제 상업 생산에서 극복할 수 있다고 보시는 쪽입니다.
예, 알겠습니다. 요거는 커서 과장님한테 얘기해가지고 So interesting about the pizza.
Yes.
When sometimes we make temper glass, there's some rolling way. In the case, the space is different.
Yeah, that's right.
Yeah. So how can we overcome such a problem?
So you're correct. If you use tempered glass, the roll-away issue, the point is you need to remove it, but you don't need to remove the roll-aways completely. So it turns out if you do the numbers, roll-aways tend to be over 100 millimeters. So if even the glass is 4 or 5 mil thick, atmospheric pressure can bend glass over 100 millimeters quite well. So as long as the roll-away is not more than something like 0.2 millimeters over 100, then the glass will actually come down onto the pillar. And the variation from pillar to pillar becomes very, very small. Not big enough for us to worry about. The problem is though...
Technically, I have experienced that when I analyze one sample from a Chinese reality maker,
Yes.
we saw that each pillars, of course, they are controlling the roughness and the roll wave of the glass itself
Yes.
very well. But when we measure the hot pressure which was applied to each pillars, this hot pressure and strains caused by this stress has been totally different.
Yes.
So some pillar has some micro cracks in here, and some other pillars has no micro pillars,
Yes.
no cracks.
Yes.
I mean, this kind of problem can be overcome
Yes.
in
But
a practical way.
It can.
That's my question.
so the question, okay. So when you design the VIG, you have to consider all of this.
Mhm.
One of the issues when you talk about the product showing this behavior is it's not just rollaways.
Mhm.
It's really a combination
Mhm.
of the bow of the glass, the rollaway, and the fact that the pillar being used is already not the same, and there are size differences within the actual pillar array.
Mhm.
So once all these combined factors come together, then we have more of a problem. Some,
제가 발표할 때 추가적으로 해서 설명 최대한 하도록 해보겠습니다.
so
또
some,
다른 질문 계속.
sorry, some of the issues, the fact that the pillar will interact with the glass no matter what. So the question you also have to ask is, how is the metal or the ceramic of the pillar interacting with the glass, but again, inside the vacuum environment, right? So if you just put any material onto glass, remember that in a vacuum environment, glass becomes very clean and it becomes very reactive. So if the glass starts to bond to the pillar, then any change in the pillar produces stress in the glass. So we don't like high contact friction or adhesion. So there's a couple of issues there, and the producers need to learn about these issues and actually need to pick the correct pillar and then look at the shape of the glass relative to that. So pillars are a real critical point, okay? Mainly because the stress concentration there is really high. Yes, sir.
Well, thank you for your excellent presentation.
Thank you.
And it was my good experience that I have met you and to see the VIG. My question is one thing that do you have any relation with the DOE or Lawrence Berkeley Lab in UC Berkeley?
Yes,
Okay,
actually,
you do.
we do. Yes.
Okay, and the window and daylight group they have.
Yes, that's right.
So we have a thumb program,
Yes,
thumb program.
yes.
So
And
we
Windows.
figure out a lot of,
Yes.
few variable there. Okay?
Yes.
So you have already talked about that.
Yes, I work. So
Oh,
I work with the daylight group for many years. So
I was in there.
Oh, okay,
Yeah,
so we should have met.
1987. Yeah.
Okay, so
Okay.
so Steve Selkowitz is retired.
Okay, that's
so
good.
Charlie is looking after the group. I
Okay.
work with them actually quite a lot right now. So
Uh-huh.
I work with them to make changes to Windows
Okay.
and Therm
Okay.
so that it will work better for vacuum glazing.
So my major is architecture. So if we want to pursue the architect designer,
Yes.
then how could you pursue them? For instance, we have to be shown that the Energy Plus program and simulation.
Yes.
So how different we did the single one and also VIG.
Yes.
So because you were the ones in the
Exactly.
yeah.
Yes.
So that makes them the designer to pick up.
Yes.
To which kind of.
So that's the purpose. So the aim, so Charlie, his group, and me and my group, as it were,
Okay.
for the last couple of years, that's what we've been trying to do.
Okay.
There is actually an NFRC standard you could call right now for a certain part of this. We have done the work for Therm, and we are finishing the work this year for Windows.
Okay.
So essentially, from the beginning of next year, the standard IGBD
Okay.
database
Uh-huh.
plus these two software
Uh-huh.
should have all of the variability for our vacuum glazing product. So any person, architect, engineer or producer should be able to use the same process that they use for IGUs to certify an VIG.
So far they don't do it yet.
No, not yet.
Okay.
For example, right now, if you go to Windows, you can pick a vacuum glazing.
Okay.
But when you pick the vacuum glazing, you can't choose the pillar, you can't set certain parameters, you're stuck with one choice. And so,
one other question is, heating loses heat transfer things, I can understand it. But how about the reflective index, or like a 3 milli is 1.5?
so Windows already has that.
Okay.
Yeah, so that's already done. So the optical part, it's all there. In terms of the solar heat gain
Okay.
and all of that actually was done
Because
first.
then the designer worry about the optical.
Exactly, exactly. So hopefully the optics, the thermal, and that's in Windows, and then the frame issue and the edge of frame and all of this from Therm, all of that should be done early next year. And so any of the qualification from the way people use the American NFRC process, that should be 100% available to the vacuum
Because
glazers.
my position, I have to pursue the art of the designer.
Yes.
So
That's
that's
right.
one of my point. Okay, thank you.
Yeah. So and hopefully the other side, the flip side of that is that the ASTM groups in the US will do those two groups will do their work,
Okay.
and they will provide the testing and specifications for the mechanical side.
Okay.
And that way, that whole North America region now has like they have for IGUs and laminated glass, they will have a complete process for a vacuum glazing product. And if someone can go through, pick a design, and then go through the testing and pass, then that product essentially is safe to use. That's the simple purpose of all of this.
We're waiting the next year.
Yes, so that-
Good job, okay? Thank you.
Keep my fingers crossed that
Thank
no one stops it.
우리 질문 또 있을 네, 질문 하나 받아보겠습니다.
일반 유리 대비 진공유리가 많이 깨지는 걸로 알고 있는데 이게 NSG 제품하고 이런데 해외 제품도 많이 있잖아요. 근데 이게 얼마 정도 일반 유리 대비 깨지는 정도 그런 건 아니에요. 유리가 깨지는 정도 그 접합 왜냐면 필러가 이거 같이 하고 있으니까 스트레스 받을 수밖에 없고.
그렇죠.
네. 그리고 이게 강화를 한다 하지만 실제 강화가 풀리가
그러니까 이제 완전히 강화를 하면 그 자체가 깨지는 경우도 있잖아요. 그렇지만 이제 또 한편으로는 이제 스페이서 때문에 이제 깨질 가능성이 있다는 거잖아요. 그래서 그건 디자인 조건이 있거든요. 그거에 대해서 얘기를 한번 해보라고 할게요.
저는 근데 해외에서는 얼마나 그게 깨지는 그 퍼센테이지
He's wanted to know the cause of the spacer. The less can be more.
Why?
It makes a stress.
Yes.
So it is possible that if you have some rating, how much the ratio. If we make 100 piece
Oh, you mean failure rate from
Yeah.
failure rate from the product or from the pillars?
From the pillars. It could be the installed.
Okay, so look, to be honest, in the design of the vacuum glazing, if you do design the pillars properly, you should see no breakages in the pillars. Okay, one of the reasons why most of the products, if you have a close look and you see some micro cracks, maybe some and not on all, and that's because there are variations. For example, the height of the pillar, or actually there could be that the pillar has not been designed right, and in transportation or handling, some areas of the glass have received more stress than others. So just simply, if everything is done correctly, the pillars should show no micro cracks. The glass should be clean. So micro cracks don't mean that the window has failed. Most users won't see the micro cracks. But we always followed a simple rule. Any micro crack means that the whole sample is dead. And that's the design rule for us. So the pillar has to be strictly designed for the product. Sorry.
The vacuum glazing is originally is a high concentration of the stress in terms of the pillar area.
Yes.
This is not a micro crack. It's just like a spontaneous breakage. It's very similar to in winter season. The temperature is very lower than the expected in Korean area.
Yes.
The vacuum glazing is not actually just not a micro crack, and it makes a
So
it's frozen.
okay, one of the reasons, maybe I misunderstand you, but if I understand you correctly, so you're giving a sort of example. So micro cracks, okay, the problem with them, and again, they're not visible. And normally if you consider what the micro crack is, it won't cause catastrophic failure. But if a micro crack has occurred in handling, and that unit is in a building and then there's cold temperature, it will continue to grow to the point where you will get catastrophic failure. And so for the design, we include things like handling and transportation. Microcracks should not be there. And if they're not there, in terms of thermal load, pillars should not be a problem. Actually, if anything, the edge of the glass should be the first area of the problem. So the pillars have a very critical design point, and they include the size, the shape, and the contact interaction, which means controlling the contact friction.
그리고 그게 제가 알면 그렇게 이해하시는 거예요. 이제 그래서 이제 저희는 필라를 선호하거든요. 왜 그러냐면 세랑 필라는 형상이라든지 이런 걸 어떻게 정하기가 힘들잖아요. 모양이 좀 뾰족하고. 근데 메탈은 디스크를 사용하는데 균일하기 때문에 그걸 눌렀을 때 이제 밴딩이 생기잖아요. 그 밴딩이 생기는 정도의 어떤 리미트값이 생길 수 있잖아요. 그것을 이제 디자인의 한계로 보고 항상 그거보다 아래쪽에다 설계를 하게. 그러니까 이제 조금 말씀드리면 이제 저도 사실은 이제 좀 이렇게 대충 하는 거라 실험할 때 이런 간격으로 놓으면 돼 하고 놓는데 그거보다는 이걸 시뮬레이션을 해보니까 그거 실험을 해보니까 이 간격이 중요하더라는 거예요. 왜 그러냐면 지금 말씀하신 것처럼 밴딩에 의한 게 있기 때문에. 근데 그게 이제 겨울이라든지 여름이라든지 날씨 때문에 오히려 이렇게 익스펜션 때문에 왜곡이 생기는 게 있잖아요. 오히려 그것이 이 필라에 의한 스트레스는 아니라는 거죠.
So again, another, Frankie said that maybe your question is different. Okay, so for example, in-service failure rates from the companies is a very big secret. Okay, I don't know the true answer to any number, but my experience with NSG is that including in-factory failure and in-service, the failure rate is less than 3%. And then, yes, less than 3%. And colloquially, you must accept that after 35 years of production and putting windows into the Japanese market, if there was a design fault where cold temperatures were causing a problem, they would have to recall. And NSG has never recalled their product. So I can't speak to the others, because the others actually don't have a very large volume of product out in the field. But NSG has a large volume and a very long time with very different temperatures from south to north. And they've not suffered. Their design on their website is that their product should not be used for temperature differences above 40 degrees. But their design actually is for greater than that. So we usually try to design up to 80 degrees. That's the safety factor aspect of the design, right? We double the point that we want to realize.
If we can, you can say that the temperature difference of up to 80%, that means
80 degrees. 80 degrees.
80.
Yes, 80.
Yes, that means thermal expansion is different between the outer span and inner pane and outer pane. So it means that the glass solder on the edge can endure the shear stress.
That's right.
Which was
Exactly.
So,
Yes. So of course, if you think about what happens, the glass on the room side is in the room, so it's not going to do anything. It's just going. But the glass on the cold side will want to shrink, and it will want to shrink a lot. And because it's bonded at the edge, that's why the glazing will start to bend. And yes, because of that, there's stresses here at the center, but there's most of the damaging stresses here at the edge. And we must pick the solder glass material and the width of the solder glass so that it will survive such a stress. And yes, you can get bad material. You can get solder glass that will not work. So you must work to find the correct formulation. And if you do, the edge is essentially as strong as the glass. That's the point, okay? Because there's no reason for making it stronger. The stress doesn't occur only in the solder glass. It occurs over the solder glass into the glass, right? So what we try to do is we make everything the same strength. So the solder glass bond and the bulk strength of the solder glass needs to be the same as the float glass.
연관 질문 하나 있잖아요. 사실 지금 이제 질문하신 분은 이거 경험에 의해서 검수라든지 이런 과정을 통해서 계속 그 효과가 발생하기 때문에 질문을 하신 것 같은데 그런 일이 없다고 하시니까 사실 더 그 부분에서 말씀드리기는 어려울 것 같고 석션 홀에 의해서 작화가 일어날 수도 있지 않겠는가라는 생각을 좀 하고요. 그리고 지금 이제 진공유리의 양쪽 면 완전 강화 유리를 사용을 하시잖아요. 완전 강화 유리는 이제 국내에서는 중유리에는 잘 사용하지 않아요. 자파 현상 때문에. 아까 그런 파손도 어떤 자파로 인한 파손도 있지 않았겠는가 생각이 되는데 이 진공유리 자체가 상당히 고가로 거래가 되고 이제 사용자들도 상당히 이제 어느 정도의 위치에 있는 분들이 사용을 할 텐데 그런 자파 발생하는 거에 대한 어떤 대책이 있는 건지
그거는 그 제가 그냥 답변 진공유리라고 해서 별 set operating what is about that?
You mean like nickel sulfide?
그래서 이 진공유리 사실은 완전 강화, 소위 말하는 템퍼드 글래스는 조금 선호하지 않고요. 소위 하프 템퍼드 아니면 스트레스라고 표현하잖아요. 그런 쪽으로 선호를 하고요. 일본 같은 경우에는 우리는 법규 때문에 그런 게 있다고 그러는데요. 제가 그쪽은 잘 모르지만 일본의 그 NSG나 마사이 같은 데는 그냥 애닐드 글래스 있잖아요. 그냥 글래스. 그걸로 하는 거를 선호하고 그렇게만 합니다.
완전 풀템퍼드가 아니어도
그거랑은 전혀 관계가 없습니다.
Nickel sulfide is, it's nickel sulfide. So the production process of a vacuum glazing is not going to make that any better or any worse. But maybe what's interesting is using tempered glass. So I think there is a little myth. So normally, I think people expect tempered glass is used to make everything stronger. It would, right? And sometimes the myth is that it makes everything stronger for the pillars. But actually, tempered glass doesn't help so much with the pillars. It helps with everything else. But the real question for us is, do we need it? So when we design the vacuum glazing and we want stronger glass, we actually don't need the glass to be 100 megapascals pre-stress. Heat strengthened 30-40 already doubles or even almost triples the inherent strength of the vacuum glazing we would like to make. Because we don't worry about the pillars as much as you think, as long as we make the correct design points. Remember, the pillars are inside the dry vacuum. The glass that might break is inside the dry vacuum, and we know very well that glass in a dry vacuum has a much lower chance of breaking than glass exposed to water and air. So this idea of strength is actually wrong unless you use tempered glass because you want safety. Okay? But please remember that our two pieces of glass are bonded together. So if one of them explodes, it's not free to expand at the edge. And so the fragmentation of a vacuum glazing is very different to the fragmentation of a normal tempered sheet. So you have to be quite careful about what safety means. In Australia, we don't like tempered glass like that. We prefer heat strengthened with lamination. To us, but America is the other way. They like tempered glass very much. So I think it's a bit of a choice.
In Korean market, it's similar. We are prefer to heat strengthened glass.
Yes.
And also in terms of, if we are talking about the details of like spontaneous breakage,
Yes.
This spontaneous breakage was done by the full tempered glass, and even though we put the full tempered glass into the vacuum glazing processing, this stress has released to the heat strength level, and also the process temperature is around 400 Celsius degree. For this case, this is automatically heat soaked.
Yes,
Heat soaked.
Exactly.
So no consideration for the spontaneous.
That's right. So this is also why Landvac or Lidas and several other Chinese, this is why they want to use metal solder, because they don't have the technology for low temperature solder glass. Anything above 400 degrees for more than half an hour and most of the temper is lost. And so using that type of solder glass or technique, you can't make tempered VIGs. So either you need the new technology, and if you don't, then you're forced to use the metal solder. And this is basically the way people make decisions.
Is your lab measure the sun heat gain coefficients?
No, we don't do that. We get other people to measure the solar heat gain coefficient.
Yeah, it's very very hard to catch the data. So
Yes, not an easy measurement.
Not your lab.
But no, we don't do that.
Okay.
So we specialize in the VIG, and that means we specialize and have our own process and equipment for, testing the mechanical strength. For example, testing one pillar on glass to look at what's going to happen. And we have special equipment for measuring the thermal performance. For example, again, measuring only the heat flow through one pillar, for example. So that's where, and when it comes to solar heat gain and things, that's why we always partnered with LBNL or NREL.
That's very important,
Yes, it is.
The sun heat gain coefficient is very important.
Yes.
So if we, when we get a simulation, if we change, a little bit, and the result is coming so different. So SGS is very important point. So I was wondering that your lab has measuring that, or
No,
you just.
To be honest, LBNL is good at that.
Oh, LBNL.
So we have always shared samples.
Okay.
We give to them. They do to be honest, they do solar heat gain, edge of frame, thermography. They do all those type of tests, and we do the other ones. And that's why we've always been partners since the beginning, to be honest.
So you let the LBNL to do that.
Yes, of
Okay,
course.
okay,
Yeah.
okay.
Even today,
Okay.
every year I send them samples, and they make measurements. And to be honest, we make arrangements. NSG, many other companies have sent them samples as well, so that they can qualify, what the product is.
LBN이라는 게 이제 UC 버클리에 있는 연구소인데요. 거기서 이제 그 열관계 이제 예를 들어서 열이라든가 PC라든가 이런 걸 갖다가 다 다루고 있습니다. 그래서 온도인 데일라이팅 그룹이라고 있는데 저도 87년도에 거기 있었습니다. 제가 교도대학에서 많이 받고 거기 가서 이제 있었는데 거기서 아마 다 이렇게 좀 중간에 교류가 있는 것 같아요. 미국의 DOE가 관리하는 연구소입니다.
So I think Dr. Kim is going to talk. So what has everybody looked at a vacuum glazing? Have you all touched a vacuum glazing? Okay. Have you all felt the temperature load? I don't think you all felt the temperature load on a vacuum glazing. So what I'm going to do is a very simple test. Sorry, can you all the way up? Yeah. I'm going to put a cup of boiling hot water here. I think you can all accept that the steam is going to be 70, 80 degrees, okay? Okay. So to be honest, it's not a very nice test, and sometimes the glass can break because the heating is so local, okay? So if it explodes, don't get scared. So the center is going to get hot, and if you can touch it after a few minutes, you'll feel nothing. This sample is one of the samples has a U value near 0.5, 0.4, something like that. So it's really insulating. You would have to wait a very long period of time. The actual water will get cold by the time. But what I'm going to do is, after Dr. Kim starts talking, which is a couple of minutes, I'm going to stop and I'm going to wipe the water off and I'm going to pass it around. What I want you to do is feel the hot and the cold side. And I want you to feel the difference, which is the best way for you to see what does it mean to have a U value of 0.4. I mean, most of us love low numbers, but I really want you to feel it because if you go away and then try an IGU, what I want you to see is, and ask yourself the question, yes, it's insulating, do we need 0.4? And what applications is it best for? And I want you to try to have a feeling memory of what something like this does, okay?